Now it turns out in this particular case, we can do a little better. Because the net force here is constant, it does make sense for us to use the arithmetic average of the initial and final x components of velocity to get the new velocity. And here's the basic idea why. We've seen that in these graphs of v sub x versus time, with a constant force, the x component of velocity for the track, in this case we're talking about the y component for the ball, changed linearly. And so if we take some time interval delta t, so here's a t1 and here's a t2, well, here's the initial v sub y, here's the final v sub y. If we say, well, we're going to use the arithmetic average, which is going to be that plus that over 2, so it'll be right in the middle, we get that. Now the distance the object moves is the area under the v versus t curve, because v delta t is a change in position. So the distance this object moves in that time interval is the area under this curve of, in distance it moves in the y direction during that time interval is that area under the v sub y versus t curve. And because it's changing linearly, this actually is the same, or it would be if I'd drawn the picture slightly better. So let's try to really draw a straight line here. There we go, that's a better straight line. It actually is the same as this area under that curve, because this area which is excluded is exactly the same as that area which is now included. They're the same, and so it's exactly correct. In contrast, when v sub y is not changing linearly, as for example the spring, so if we had something like this, then we could do the same thing. Here's our delta t, t1, t2, vy initial, vy final. The area we want is this area under this curve. That's going to be how far it went. But if we use the average of these two things to predict it, what we're going to get is that area. And it is really not the case that this and that are the same. They're not. So in fact, if we use the arithmetic average here to predict what we want as the area under the curve, it's going to be really wrong. And so constant force component, constant change in velocity is really a very special situation. But because it is, we can do something sort of interesting. So let's see what we can do with our kicked ball here. We can write some algebraic equations that are going to let us predict where it's going to be at any time, just using the momentum principle and what we know about how to update position using velocity. And these equations may end up looking, so we start with the idea that the net force in our case is going to be 0 minus mg0. But let's just write a general situation. So we've got this force in the y direction but not the x direction. We're going to talk about the ball we kicked. Let's think about the x component of the ball's motion. So we have F net x is 0. So we have Px final is Px initial plus 0. And so we just have x final. So we have Vx final is Vx initial. X component of velocity isn't changing. And so to calculate its position, we can just say the final position is the initial x component plus v sub x initial delta t. So we just take the initial x component of its velocity. In this case, it was 3 meters per second. Multiplied by the time, that's how far it goes. Now, y is a little more interesting because f net y is not 0. So we have px in the future, y. P sub y in the future is P sub y initial plus f net y delta t. And so dividing through by the mass, because in our situation, P sub y is going to be 1 times m v sub y. Gamma is surely 1 at these small speeds. So we can say we have Vy final is going to be Vy initial plus f net y divided by the mass times delta t. We've just divided through by m here. Okay, so now we know that this is changing linearly because the force is constant, so we can use the arithmetic average. So we can say that Vy average during this time interval is just Vy initial plus Vy final divided by 2. And that's Vy final, so we'll substitute that in there. We've got Vy initial plus the quantity Vy initial plus f net y over m delta t, this whole thing over 2. So we just plug these values in for Vy final. And so that comes out to, okay, there are 2 of these divided by 2, so we get a Vy initial plus a half f net y over m times delta t. So this is going to be the average y component. Okay, so now we want to predict position, so we're going to use position update. So we say y final is y initial plus v average y delta t. And so that's the initial y position plus this thing. So we have Vy initial plus a half f net y over m delta t, all times delta t. And so we write this out, and so we have the initial y position, and then we have the initial y component of velocity times delta t, and then we have a half f net y over m, and we've now got a delta t squared. So we have a quadratic equation that tells us how we can calculate the final position for any delta t. We just need to know where it is at the beginning of the interval and what its y component of velocity was at the beginning of this interval, and then the force, and we can figure it out for any delta t. So that's pretty general. Now in our situation, we can simplify it even further because we know what the net force is. It was actually just this gravitational force. So we can plug that in. So we have here f net y is a negative mg. So we have y final is y initial plus vy initial delta t, and then we have plus a half times a negative mg over m delta t squared, or y initial vy initial delta t, and we have, it ends up being a minus g delta t squared for this ball that we've kicked in the air. Now, would this equation work for the mass on the spring, bouncing up and down the mass on the spring? No, because the force isn't constant. But in a situation where force is constant, it works. And so we could figure out the position of our ball 3 seconds after we kicked it, a second after we kicked it. Have to be a little careful, because of course we could give it some arbitrarily long time, and the equation doesn't know that there's the ground there and the ball's actually going to stop or bounce when it hits the ground. So if we plug in a time longer than it takes it to hit the ground, we could get a negative number for its position. But we could also solve this. If we say, well, y final is 0, we could solve for the time it took to hit the ground. So we could do various things with it. So again, this is a special case, but it is a case that's kind of nice to work out because we can do it algebraically. It's called an analytical solution if we can work it out algebraically. Do you have questions about this? Comments about this?